Next, we're going to look at some worked examples involving electrochemistry. The first question asks us to design a galvanic cell that uses this redox reaction. And we need to identify the anode and cathode half reactions and sketch the experimental setup. Okay, the anode is where oxidation occurs. Okay, so we can see that chromium is losing electrons because it's becoming more positive. Electrons have a negative charge. And tin is gaining electrons to go from tin 2 plus to tin 0. Okay, so to balance this equation, we want our electron term to drop out. So chromium is losing 3 electrons, tin is gaining 2, and the least common multiple would be 6. So we multiply the first half reaction by 2 and the second one by 3, and this gives us our balanced equation. Right, so this is a diagram of what the galvanic cell should look like. We have a chromium anode, which is immersed in a solution of chromium-3 ions, and then we have a tin cathode, which is immersed in a solution of tin-2 ions. We have a salt bridge, which allows the transport of sodium ions and nitrate ions. And electrons will flow from the anode to the cathode. Right, interpreting the shorthand notation for a galvanic cell. Okay, the two elements that are undergoing oxidation and reduction are tin and silver. Platinum is an inert material which is used to conduct electricity, and this is actually not part of the half reaction. Okay, the reason that we need the platinum electrode is that both forms of tin are in solution. Okay, and since they're in the same phase, we separate them with a comma rather than with a vertical line. Okay, so tin 2 would be the anode, and silver ions would be the cathode. I'm sorry, silver metal would be the cathode. Okay, so here's the half reaction involving tin 2 and tin 4. We're losing 2 electrons. Each silver is gaining 1 electron, so we need 2 silvers. And so the overall reaction is tin 2 plus 2 silver ions produces tin 4 plus 2 silver atoms, or silver 0. Okay, problem 3 involves calculating a standard free energy change from a standard cell potential. Okay, so we have the standard cell potential at 25 degrees Celsius is 0.90 volts for this reaction. Calculate the standard free energy change at 25 degrees. Okay, for this, we would just use the formula delta G standard equals minus NFE standard. Okay, we do need to know what N is, and each aluminum is gaining 3 electrons. And there's 2 aluminums, so that would be 6 electrons. So N would be 6. F, of course, is a constant. It's 96,500 coulombs per mole. And we fill in the information here. This is a conversion factor for converting volts to joules. Okay, so this is negative 5.2 times 10 to the 5th joules, or negative 520 kilojoules. Okay, so that indicates a spontaneous reaction. When delta G is negative, the reaction is spontaneous. But when E is positive, then it's a spontaneous reaction. Okay, here, arranging oxidizing and reducing agents in order of increasing strength. Okay, so what we do is we can just rely on this table. The strongest oxidizing agent in the table would be fluorine gas. The strongest reducing agent is over here on the product side, that's lithium. And the stronger the oxidizing agent, the higher up on the chart it is. Okay, now when an oxidizing agent participates in a reaction, okay, the key word is agent. It oxidizes something else, but in the process, it gets reduced. Okay, so the more positive the potential, the stronger the oxidizing agent we have. Okay, and the strongest oxidizing agent has the greatest tendency to be reduced. The strongest reducing agent has the strongest tendency to be oxidized. Okay, predicting whether a redox reaction is spontaneous. Okay, predict from the table whether lead-2 can oxidize aluminum or copper under standard state conditions. Okay, so here's lead-2, and aluminum is down here. Okay, so the higher up on the chart, the more easily reduced it is. So lead-2 would, in fact, oxidize aluminum. Okay, what about copper? Okay, copper is actually above lead-2, and so lead-2 would not oxidize copper. Okay, and we can prove that quantitatively. Okay, so if we assume lead is the reduction, then we use the standard E value as is. And if aluminum is undergoing oxidation, okay, in the chart, aluminum is listed at negative 1.66. So since this is an oxidation, we would change the sign. Okay, we would add these together, and since the overall cell potential is positive, then this is spontaneous. Okay, here, if lead is being reduced and copper is being oxidized, okay, for the oxidation, we change the sign for the value that's in the chart, and the overall cell potential is negative, so this reaction is not spontaneous. So lead would not oxidize copper metal. Okay, this is using the Nernst equation to calculate the cell potential under standard state conditions. Okay, so under non-standard state conditions. Okay, so the Nernst equation, we would want to calculate Q. Okay, so that is products over reactants. We would leave out the zinc solid, and these are the conditions. Okay, we would want to calculate the standard potential. Okay, so hydrogen is 0. Zinc is negative 0.76 for the reduction, but zinc is actually undergoing oxidation, so it would be positive 0.76. So the standard potential would be 0.76. Okay, so this is the equation we would use. We're looking for the non-standard potential, and we would calculate Q this way. It's zinc concentration times the pressure of hydrogen gas divided by the hydrogen ion concentration squared. Okay, we can see that there are 2 electrons being transferred, so N is 2. Okay, so doing the calculation, okay, these are the values that we filled in. Standard potential for this reaction is 0.76. And so the non-standard potential is 0.88. Okay, since this is more positive than our standard potential, this tells us that this has a greater tendency to occur than under standard conditions. Okay, well that should make sense. We've got very little product and a lot of reactant here. Okay, so we've got this galvanic cell with silver and lead. What is the change in the cell voltage on increasing the ion concentration in the anode compartment by a factor of 10? Okay, so this is the overall reaction. And okay, Q would be the lead concentration divided by the silver ion concentration squared. Okay, we're looking for the change in E. Okay, so if we increase the lead concentration by a factor of 10, okay, so this is compared to standard conditions, so this would be a 10 to 1. Log 10 is 1, so E equals E standard minus 0.03. Okay, so this change would decrease the cell voltage by 0.03 volts. Okay, what if we increase the cathode compartment by a factor of 10? Okay, then we would square the 10, and log of 10 to the minus 2 is minus 2. And so our non-standard voltage, or our voltage would increase by 0.06 volts. Okay, so here we have a cell with a potential of 0.55 volts at 25 degrees. And Okay, in the cathode compartment, we have mercury 1 chloride and mercury liquid metal. Okay, what is the pH? Okay, pH is minus the concentration of the hydronium or hydrogen ion concentration. So once we solve for this, we can then find the pH. Okay, so this is the overall reaction. Hydrogen gets oxidized, mercury gets reduced from +1 to 0, and the standard potential here is 0.27, or 0.28, I should say. And so the overall cell potential is 0.55. So if we take the difference, that is the cell potential in the hydrogen compartment, 0.27. Okay, so using the Nernst equation, okay, we want to calculate the pH here, and we're given that the pressure of hydrogen gas is 1. Oh, let me go back. Okay, there's 2 electrons being transferred. The standard potential, half cell potential for hydrogen, the hydrogen electrode is 0. Okay, under these conditions, we see the half cell potential, or the anode potential here is 0.27. Okay, so if we solve for H plus, and then we take minus the log of that, that would be 0.46. So actually, this is the log, and so once we solve for that, we can find the pH. It's 4.6. Okay, this is using standard reduction potentials to calculate an equilibrium constant. Okay, so to find the standard potential here, okay, we would locate dichromate. Okay, that's right here. It's 1.36 for the reduction of dichromate, and dichromate is being reduced. It's going from +6 to +3. Bromide is getting oxidized. It's losing an electron, going from -1 to 0. Okay, so dichromate is here, and bromine is down here. So that is 1.36, and then we would change the sign of our species getting oxidized. So 1.36 minus 1.09. So that should be 0.25. And to find the equilibrium constant, we could use this equation. Actually, it's 0.27 would be the okay. Well, anyway, okay, we would set up the equation this way. There's 6 electrons being transferred, and so log K is 27, so K is 1 times 10 to the 27th. All right, in this question, a constant current of 30 amps is passed through an aqueous solution of sodium chloride for 1 hour. How many grams of sodium hydroxide, how many liters of chlorine gas are produced? Okay, if we take 30 amps and we convert hours to seconds, so that's 3,600 seconds. An amp times a second is a coulomb. Okay, so we take current times time to find charge, and then using the coulombs, we can calculate how many moles of electrons that is. And then using stoichiometry, we can calculate moles of product. Okay, so if we calculate our charge by taking the amps times the time, an amp is a coulomb per second, we get 1.08 times 10 to the 5th coulombs. Okay, if we take this many coulombs times Faraday's constant, that gives us the moles of electrons. Okay, so the cathode reaction yields 2 moles of hydroxide per 2 moles of electrons. Okay, so it's a 2-to-2 ratio. And so 1.12 moles of electrons would yield 1.212 moles of sodium hydroxide. Okay, to convert to grams, we would simply use the molar mass of sodium hydroxide, so that's 44.8 grams. Now, in the case of chlorine, it requires 2 moles of electrons to produce 1 mole of chlorine gas. And so we know to divide by 2 because we want our moles of electrons to cancel out, so that we get this many moles of chlorine gas. At standard temperature and pressure, 1 mole of gas occupies 22.4 liters, and so our volume is 12.5 liters of chlorine gas. Okay, this is calculating the current required to produce a given amount of product. Okay, so we would proceed through the sequence of conversions in a similar manner, but we would actually go in reverse order. Okay, so we want to produce sodium metal at a rate of 30 kilograms per hour. Okay, so 30 kilograms of sodium, would be 1.30 times 10 to the 3rd moles. And it takes 1 mole of electrons to produce 1 mole of sodium. Okay, so that's also how many moles of electrons we're using. Okay, so 1.30 times 10 to the 3rd moles of sodium. And there's 1 mole of electrons per mole of sodium. And there's 96,500 coulombs per mole of electrons. Okay, so moles of sodium, moles of electrons cancels out. And this is our coulombs. To get the current, an amp is defined as a coulomb per second. So we would take our total charge divided by our total time, and our current required is 34,700 amps.